Let me welcome everybody on the next talk in the series which commemorates Polish mathematician Rejewski, Różyckiego and Zygalski, who broke Enigma code. This series of lectures was established in 2008 to commemorate 75th anniversary of breaking Enigma code, which happened 1932 or 1933. Probably this was a sort of top secret date where they really first broke this code. And then in 2008, a Faculty of Mathematics and Computer Science, together with Mickiewicz University, decided to commemorate this achievement by establishing a series of lectures, for which we invite basically the top computer scientists and some historians as well. So let me just thank our sponsors. So let me thank the Vice President of the University, Michał Banaszak, and the Dean of the Faculty, Thomas Shen, who is somewhere here, and yes, over there. And let's go to the lecture. So let me just invite, let me present our today's speaker. So Professor David Gamarnik was born in the state of Georgia, and I mean this Georgia who is to the east of Poland, not to the west of Poland. But all his higher education was in US. He was a student in New York University, Curran Institute, and then he got a PhD from MIT. Then he worked for some time in IBM Research Center and became the full professor in MIT. And Professor Gamarnik is in a way very special because, as far as I remember, none of our speakers were really working in operational research. This is the main topic of David Gamarnik, who got several prizes from INFORMS, which stands for Institute for Operational Research and the Management Sciences, including Airline Prize. But this is only one part, so don't be scared about this operational research. This is only one part of a variety of research interest of David Gamarnik, who is doing quantum computing, stochastic process, machine learning, test theory of algorithms, and many others. So as for today's talk, as you see, it fits very well to the topic of our series of talks, because our aim was not only to present the recent advances in computer science, but also put it in a sort of larger perspective. So as you see, we will now connect computer science with part of physics, mathematics, and maybe more. So once again, thank you for accepting our invitation, and David, the stage is yours.
Thank you very much. It's a huge honor for me to be delivering in the series of lectures dedicated to the amazing work done by Rejewski, Różyckiego, and Zygalski. I had to practice, of course, to pronounce those. Thomas was very helpful. I'm also reading a book by Kozachuk and Strajuk about the development, but apparently the book is not so good. So now I got a better book to read. So I have something to do on the plane, and I very much look forward to it. Since you mentioned operations research, it's actually a lesser known field, but it actually has to do with the World War II, just as much as the work on Enigma. And it marks the birth of the field called the linear programming, which might be somewhat familiar to you by George Dancing, and he was trying to help the Navy to do the scheduling of ships. So wars are horrible, but they bring maybe sometimes the best in humanities in many ways that you see in the names of these wonderful, amazing individuals in the fields like operations research and so on. But let's hope that we have this wonderful development which are brought about by peaceful reasons and not because of the war. Now let me get to my talk, and once again my deepest gratitude to my hosts for the opportunity to do that. Let me start with the title. I apologize for the long title, but I'm a disciple of Russian literature, and if you ever read books by Tolstoy and Dostoevsky, you'll notice that the sentences are very long. And by the time you get to the end of the sentence, you forget what's in the beginning. I hope that does not apply to this talk. I hope that the beginning and the end will have some kind of a meaningful connection. The next thing I need to do is explain the faces here. These are not my collaborators. This is Alfred Nobel. This is Niels Abel. Obviously, I don't need to explain to you who those are. And this is Turing, kind of dropping in the shadows of these two individuals. And that's in the title that I owe you some explanation. What's the genesis of this talk? I'm also now writing a survey article with the same title. Hopefully it will come out soon. Let me get to the talk. A few recent historical developments. In 2021, Nobel Prize in Physics was awarded to physicist Giorgio Parisi for discovery and interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Okay, whatever. In just this year, 2024, the Abel Prize in mathematics, so now we are somewhat closer to the world of mathematics and computer science, was awarded to Michel Talagrand, who is probably known to some of you as outstanding probabilist, for the groundbreaking contributions to probability theory and functional analysis and outstanding applications to mathematical physics and statistics. And nowhere in these citations you will see a mention of the computer science and algorithms. Perhaps that makes sense because, one is a prize in physics and another one is a prize in mathematics. But as a matter of fact, both of these individuals, the ideas stemming from those individuals had a profound impact in the field of algorithms and computations, optimization specifically. And this is what I want to devote this talk and share with you some developments. The genesis of it came from this work of two amazing individuals, but I also will use this as an opportunity to credit lots of lesser known but outstanding people, some collaborators, some are not, who have contributed a lot. I'm going to frame this talk as a hypothetical dialogue, if not a debate. Not a fight, but kind of a debate between a computer scientist, a hypothetical computer scientist. This is Turing, obviously, and I don't need to tell you who's this person. Computer scientists and physicists talk. This is actually pretty close to reality in a way that I will explain. The computer scientist says, I'm a computer scientist. I'm interested in computations and algorithms. You're a physicist. Is there anything you can tell me as a physicist that I didn't know and that I might find interesting? And the physicist, the response says, okay, I'll help you out, but maybe you can help me out as well. I'm a physicist, I'm interested in understanding the properties of matter. Computations is just a tool for me, right? But my goal is to understand the nature. Is there anything you can tell me as a computer scientist that I didn't know and I might find interesting. Historically, up until fairly recently, it was a one-way dialogue where the tools from physics were enriching and helping and bringing new ideas to the computer science. And most of the talk will be about that at a very high level, of course. But also recently, certain things that emerged from the field of computer science are of interest in physics as well, to the best of our understanding and knowledge. I'm not a physicist, not even computer scientist, strictly speaking. My degree was in operations research, but I'm like a shuttle who sort of runs between different fields. So let's get to that. In this dialogue, we will play the role of computer scientists mostly. So we will be Turings of the world. What do we want? As a computer scientist, we want algorithms. We want algorithms, and for the computation, somewhat narrowly focused in the field of so-called combinatorial optimization, say optimization on graphs. By the way, let me invite you to ask questions along the talk. I don't know if that's physically, if this is allowed with the rules, but I'm totally welcome interrupting at any point and asking questions. That's totally fine. Right, so we want optimization. I'll give you several examples of those. So we want to solve some optimization on graphs. We want to do that fast. And canonical way to call something fast if your algorithm runs in the so-called polynomial time, so you don't have to wait for the end of the world until your computation actually gives you something. The great theory of computational complexity says that for most of the problems you might care about, this cannot be done if you believe that the class P is not equal to NP, and majority of your computer scientists, probably you've seen this famous or infamous conjecture that P is not equal to NP, so we don't expect to solve those problems fast in polynomial time. Nobody proved it, but we strongly believe in that. But that's not the point. The point of this talk is that maybe we don't want to be that ambitious, and maybe we want to solve these problems typically for most of the instances, most of the graphs, defined in some reasonable way, right? Can we do that? In other words, what if our model for computation for which we're doing some kind of algorithmic procedure is random and not generated by adversary? In that case, the conjecture P not equal to NP, even if it's correct, probably is correct, is not of help, because it tells us we cannot solve these problems for any adversarial instance. But for typical, that's a different story. Why and what's the motivation and application of that? Along the way, I'll say a few words about that, I might. But it's by itself, I think, an interesting question. Okay. So let me share with you some 3 examples. I'll try to make those as elementary, as accessible as possible, so hopefully everybody will be on board and understand what are the challenges. The first example has to do with the task of packing spheres in graph. We, combinatorial optimization folks, call it independent set problem, but let me call it also sphere packing, that maybe makes a little more sense for outsiders. So here we have a graph. What's a graph? Nodes and links. In these nodes and links, the sizes of the nodes is irrelevant. The length of the links is irrelevant, so there is no geometry here. It's just who is connected to whom, like in the Facebook friends. You connected or you're not connected. That's the information that is conveyed in this graph. What we want to do is we want to pack spheres such that they are not sharing an edge. We want to pack non-friends in this graph. We want to find the largest collection of non-friends in a Facebook or whatever media your preference is, for whatever reason. This is an NP-hard problem, right? But this is a small enough graph. I had nothing to do a while ago, so I decided to actually find the largest number here. Actually, a small enough graph, you can find it, it's 10 nodes. I think that's correct, but if you find a better solution here, I wouldn't be surprised. I'm not very good in solving these little problems. But you see, the old spheres here are none to share an edge. Fine, 10, we can do 10 here. What if the graph was larger and random? Right. So the graph is larger, but we don't assume anything about that. As I said, it's NP-hard, case closed. But if the graph was not adversarial, but generated according to some randomness mechanism, and here let's assume the simplest randomness mechanism we can imagine, it's called Erdős-Rényi graph. Again, something is probably many of you have seen, but let me not assume that. This is a model of the graph where every link is there with equal likelihood for all pairs and independently between pairs. This is a celebrated Erdős-Rényi graph. If we want to do sphere packing in Erdős-Rényi graph, what can we do algorithmically? It's an interesting problem that was addressed by Dick Karp in 1976, almost immediately that he discovered his famous NP-hardness of all kinds of problems like traveling salesman and so on, whatever he's famous for. He immediately became interested in random graphs and solving optimization of random graphs, and he realized that in fact a very simple algorithm that I will explain, a very stupid algorithm I should say, actually gives you half optimal. So if the largest number of spheres you can pack in this graph is 10, this algorithm will guarantee to find you 5. If the largest number is 30, it will give you 15. Roughly speaking, asymptotically, a lot of detailed mathematics here I'm going to ignore. Right? And the algorithm, let me share with you the algorithm. It's actually quite stupid, and I will stress the word stupid. You'll see why. Here's an algorithm. You just pick your node, completely at random, blindly, and you put it into your independent set, into your collection. So you put this node. Because you put this node, you have to you drop the neighbors, because you cannot put this node here, you cannot put this node here, that would violate the sphere packing requirement. So you drop those two nodes. And then you go to another node, like this one. You have to drop the neighbors. Then you go to another node, there's no neighbors, another node, no neighbors, another node, two neighbors, you delete them, another node, no neighbors, another node, two neighbors, delete them, and you get 7. Question. Am I allowed to ask questions to the audience?
Well,
Okay, all right.
yours, David.
What's so stupid about this algorithm? Any kind of suggestions? Be brave. You don't have to be right. Right.
Maybe.
Yes?
It removes nodes that we could count as these spheres while they are needed. We need to count them, yeah? And if they are removed, then they are removed from the overall count of the spheres. Like you mentioned that you have one sphere here, one node here, two nodes here, and other node here.
Yes.
So these two should be in the answer, but the second one is removed.
Wow, you are faster
The
than
last step.
in the last. Okay, you're faster than me, and I think your answer is correct. The algorithm makes some stupid choices, like first. Okay, so this is the wrong one. It starts here. You probably want to start here or start here. There's some cleverness that you might want to use in doing this algorithm, right? Because you don't want to destroy too many neighbors, right? And if this one has 2 neighbors, maybe you don't want to start here and so on. But the algorithm ignores that. But that's a very correct answer. The algorithm ignores that, and oops, that's too fast. But even if you, however stupid it is, it gives you half. The problem is that nobody improved it. There is no better algorithm. No better algorithm that we know of. That's depressing, that we cannot improve on this apparent stupidity. But if this was an isolated story, that would be just half of the problem. The problem is that the story prevails lots of other examples. Let me share with you 2 other examples. This is the example of this so-called constraint satisfaction problem, famous K-set problem, which is the mother of all NP-hard problems, where you have Boolean variables, clauses, like 3 clauses here, and there are conjunctions, and your goal is to assign values to those variables and their negations to make the whole formula true. This is an NP-hard problem. But what if the formula was generated randomly, and not adversarially? Turns out a very similar story, but it's slightly more complicated. To the extent that the ratio of clauses to variables, so how many clauses you hear? You have 1, 2, 3, well, you don't know how many. The ratio of clauses to variables is at most some number which depends on the size of the clause. We know the solutions exist with overwhelming probability, but this is a non-constructive fact. We prove that solutions exist, we cannot find them. If you actually want to find them, you have to sacrifice a significant factor here, which grows as the size of the clauses grow as well. So before we had half optimum, now we have log k over k optimum. Of course, none of these details, mathematical details, are important. What's important here to keep in mind is that there is a gap between what we can do algorithmically and what the truth is, and we want to understand it. And the example number 3, and once again, feel free to interrupt me with questions if something is not clear. Now, this is the problem that actually originated in physics. This is a problem of optimizing Gaussian points associated with the hypercube. It's not terribly important to understand details, but let me share with you some of it. We have a bunch of independent standard normal random variables which are arranged in a big tensor. And then for whatever reason, we need to do optimization of the following kind. What we do with optimization is we optimize over the elements of the binary cube, plus, minus, ones, or bit strings. Each bit string is associated with some product like this. And we want to find, so sigma is, blue color is what we optimize over, is something we want to maximize over and find the largest value. This is probably a problem that's not familiar to majority of you, unless you've had some exposure to physics. And it looks a little scary in here. So let me represent the same problem in a somewhat friendlier way, in a picture way. It's hard to do geometry here, but to the extent that it's possible, let me do it like this. So this is my picture of a binary cube in n dimensions. It's a little hard to draw, but this is my best effort. So corners are bit strings here. We have 2 to the n corners. Each of this corner is associated with Gaussians. So we have the whole bunch of Gaussians. This is Gauss. For each corner we have a Gaussian. Now because Gaussians can take positive value and negative value, I've decided to flip some of the Gaussian to indicate the negative sign here. Right? So we have 2 to the n Gaussians, we want to find a point with the largest Gaussian. The reason it's not trivial is because these Gaussians are correlated. Through the formula that I gave earlier, they are correlated. It's not these Gaussians that you maximize. You need to do the sum product. Anyway, some hard, potentially hard Gaussian optimization, maximization problem. As it turns out, this can be rephrased as the problem of finding a maximum cut in a graph with Gaussian weights. That can be done. How? It's not too complicated, but boring, too boring for maybe for this talk. This can be done, not too hard. And arguably, because of this connection between graph optimization and the problem which came from physics, this is the problem in the spin glass theory of spin glasses, that maybe for the first time brought together a physicist and a computer scientist to the same table, because they realized actually we're looking into similar questions. And that's fascinating. So at least we have something to talk about here. Okay? What do we know about this problem? You've noticed that in previous two problems, we always know the answer. We can predict the answer probabilistically. And then we can say, okay, can we get to this answer by algorithmic methods? And there was a gap. So let's see, let me share with you how this works out in this third and a final example. This is a final example. I'll stop torturing you with examples. I promise. Well, in fact, the optimal value for this problem is what Parigi was credited in the Nobel Prize. He said something like this. Well, first you need to normalize the objective value, maximal value somehow, and then here's the answer. It doesn't matter what the answer is. The point is that there is an answer. Some differential equation, some variational problem, you need to do some mumbo jumbo. Once you do that, you find the answer. Important thing here is that the answer depends only on P. So you need to solve some differential equations. You can numerically solve it. It's doable, and it was done for P equal to 2. This is what you get. So that's what Parigi did in 1980. And what Talleyrand did in 2006, he said, actually you're right. Because Parigi's work was conjectural. He introduced physics method, but non-rigorous. He said, I predict the formula, the answer is this. I cannot prove it, but I strongly believe it's true. And what Talleyrand said, I actually have the right mathematics to do that and prove it. Okay? So that's wonderful. You use a little formula, you conjecture it, you get the Nobel Prize. You prove it, you get the Nobel Prize. Not bad. Right? But what about the algorithms? For a long time, we didn't have any non-trivial algorithms that would give us something interesting. And dramatic progress was achieved, in fact, only 5 years ago by two somewhat younger people, Subak and Montanari, who discovered an algorithm that in fact reaches optimality for this Gaussian maximization problem when P is 2. But did not do that when P is larger. Any questions so far? Now we're going to switch gears and talk about what physics can bring to the table that might be of help to understand this somewhat depressing conundrum. I gave you 3 problems only. In fact, there is maybe at this point about 20 or 30 problems of a similar kind. We know the optimal value, we have the best algorithms, and there is a gap. We need to understand this gap. What can physics tell us about that? back in 1986, two physicists, Fu and Anderson, they have, on behalf of all physics community in a way, committed to be of help. They said, we actually believe we can explain what's going on in here. And they said, this is a quote from the paper, we propose to study the general properties of such problems, combinatorial optimization with the random structures, in the light of the structure of the solution space, the existence and the nature of phase transitions. This was kind of interesting because this is not how we canonically usually understand algorithmic hardness. We understand algorithmic hardness from reduction. Reduce traveling salesman to independent set to coloring, coloring to matching in hypergraphs, and so on and so forth. Their proposal is different. They said, let's do it differently. Let's do it physics way. Phase transitions, solution spaces, and whatnot. So they have committed to help, but the first serious attempt to help came about in the 90s. I've quoted here a few papers mostly by physicists, I think actually all of them are physicists, who put forward various explanations for why those problems are hard and what prevents us to bridging this gap. And the explanations were of the form, well, you need to look at the phase transition, whatever that means, and see if it's continuous or discontinuous, whatever that means. Or you need to see in the context of the satisfiability problem. Remember, the satisfiability problem is a little special because you either have a solution or you don't. This is kind of a yes or no situation. You need to see how close to non-satisfiability you are and see how much time, and the time will progressively become large as you get close, but as you are away, it will become easier. We don't have to split our hair about the value of these approaches. Most of them turned out to be wrong predictions, wrong in some sense, didn't pan out. However, the efforts paid off. And then in early 2000, there was a completely different proposal. That turned out to be more fruitful. It came now in a mixed form. Some of it came from physicists. In parallel, it was by computer science. So those people are physicists, but Dmitry Saklioptis, one of the front runners of this field, is a computer scientist. They said, and that was inspired by Parisi's work, they said the following. So let's remember the K-set problem. I'm just going to remind you that we are in the setting of the K-set. That means that we have these clauses, x3 or x7 negation or x10, and then you have clauses like this, generated randomly, and we want to see when the solutions exist, when it's not. First, we know this. What is this vertical line? We know that as you pack more and more clauses, at some point, you will not be able to find a solution. They simply do not exist with overwhelming probability. That's something I already mentioned earlier. Right? And I gave you a constant, 2 to the k, some number. We know once you pack more clauses than this number per variables, you simply don't have solutions. So this we know. But then they discovered this line. And that's an interesting line. What they showed, conjectured, and proved that in this line marks a phase transition of a different kind. Below this phase transition, if you look at all solutions, So these are all Boolean assignments that satisfy your formula. It looks like a connected set, in a sense that you can go, these are bit strings, you can go from one to the other, to the third, and so on, in an uninterrupted way. Probably. But once you go above this threshold, then the solution space looks different. It becomes shattered or clustered. So you have a bunch of solutions in one space, part of the space, and then a bunch of solutions in a different one, and a different one, and so on. So it looks geometrically completely different. The most remarkable thing about this, okay, let me say one more thing about that. There is a feature of this, which is called overlap gap property, which simply says the diameter of each cluster is smaller than the different distance between the clusters. Okay? For now, this seems like the curious properties of this cluster. So what they have this property. It will play a more important role down the road. But the most remarkable thing about this line is that that's exactly the line where algorithms stop working. The threshold that I quoted earlier, where you can algorithmically find the solution, is only up to that ratio of closest to densities. Above that, would fail. Now they've discovered that above this line, something else happens in the solution. So it was kind of a first smoking gun. We kind of see, at least coincidentally, that at the moment when algorithms fail, we have a change in structure of the solution space. And that was by itself a remarkable breakthrough, for hopefully understandable reasons. All right? Where can we go from here? How can we use that? Are these clusters responsible for the algorithmic failure? Is this space transition responsible for algorithmic failure? It would be great if that was the case. It would make my talk simpler. Right? Certainly that would be nice. Truth is sometimes more complicated than that. So the answer is only yes, but partially. Strictly speaking, it's not the clustering that is the obstruction to our success. It is the fact that these clusters exhibit this property. The diameter of each cluster is smaller than the distance between the clusters, the overlap gap property. Why is it called overlap gap? I'll talk about short. That was a property that turned out at least to be useful and responsible for the apparent failure of the algorithms. I should tell you something I've done in this space. This is what we have done with my great collaborator Madhusudan. So I put his picture, he's my collaborator. I felt that I should show you his face. Where in 2014 we proved that in fact this property is a barrier to algorithms. Well, not all algorithms. We cannot barrier all algorithms, because if we did, we would prove P not equal to NP. Even an average problem, that's too ambitious. But for certain big class of algorithms, it was possible to do. Right? And the property that enabled us to do that is this property overlap gap. Let me paraphrase it again what it means. In fact, it means something very simple. It means every two near optimum solutions are either close to each other or far from each other. They cannot be in between. How so? If I go back to here and here, they are close to each other if they're sitting in the same cluster.
If they're sitting in different clusters, they are far. But there is no pairs of solutions which distance larger than this and smaller than this, simply because of the topological structure of these clusters. And that turned out to be a useful property to rule out some classes of algorithms. Since then, the classes of algorithms expanded to bigger and bigger, and now it includes more than local algorithms. Whatever local algorithms means, that let me not get into this. Let me say make a quick comment about how do you prove things like that. This talk is not about proofs, but let me still say a word. You might think that this has to do with some, I don't know, solving differential equations, maybe topology, or differential geometry. No, you don't have to go that far. All the proof techniques you can find is based on something called first and second moment, and you can find it in this book by wonderful Polish and Swedish authors, two of them conveniently present in the audience. First and second moment method, I'm not going to tell you what it is. If you don't, go to Tomasz and Andrzej and learn it. It's powerful and elementary at the same time. And most of the proof techniques that we use relies on that. Nothing super sophisticated is needed. It doesn't mean it's not deep. It's very deep. Method goes back to Erdős. It's very deep, but it's elementary, in a good way. Probably I'm preaching to the choir here, so maybe most of you have seen it in one form or the other. And it's also my table book. It's a wonderful book.
But not very sophisticated.
I'm
But not very sophisticated.
And that's good. That's good, because, you know, maybe the best ideas in physics are also in a way not so sophisticated, because it needs to be, nature doesn't speak to us in super complicated, 150 pages proofs. It should be more simple than that. All right, so let me continue. Let me share with you a simple idea why the property like this is a barrier to algorithms. And I'll do it just purely by pictures, no math, strictly speaking. So the important idea was to realize that this property, the short distances or large distances, holds not just for one random graph, but across a manifold of graphs, many copies of graphs, so to speak. And that was that important, technical but important remark. So what do I mean here? Imagine that you play the following game, or imagine you're doing the following simulation experiment on your computer. You simulate a graph. It's not hard. You just generate a random matrix of adjacencies. That's not hard. Let's say this is the graph. Some edges are here, some edges are not here. Fine. That's your graph. And then you start resampling edges, one by one, in any order. It doesn't really matter in which order. So for example, you resample this pair and this edge is no longer there. Then you did it again, and now this edge is here, and it was not here before, now it's here. Oh no, sorry, this one, it was not before, and now it's here. And then you do it again, some edges is gone, some edges are present, so you're doing this reshuffling, random reshuffling. Do it again, do it again, do it again. If you do it many times, what's going to happen in the end? You're going to have a new random graph copy, which has nothing to do with the original random graph copy. You've resampled everything. Okay. The simulation hopefully is clear what we're doing here. Nothing too sophisticated. Now let's do the following thought experiment. The thought experiment, which you can realize perhaps in simulation, is the following. Pick any good hard sphere packing in this graph. One close to optimality. That's, of course, it's hard to do because that's a hard problem. But let's say you do a lot of brute force estimation, or use a Groby optimizer, you spend a lot of time, you find it in this graph. One such solution. There's many, but one such good solution in here. And you put it it's a bit string. Then you find another one, it's a bit string. And for the next graph, it's a bit string, another bit string, another bit string, and you keep doing that. For all of those graphs, you find bit strings which are respective good solutions in the respective graphs. Okay, and finally for the last one, this graph is nothing to do with good graph, it has its own good solutions. An interesting thing is that those solutions are clustered as well. And they exhibit the overlap gap property as well. So this property of small diameter and large distances is not just a property of one graph, it's a property of the whole collection of these correlated graphs. And that can be used to pit it against algorithms thanks to the following rather simple idea. If the algorithm, provided the algorithm has only one simple feature, I want the algorithm, I'm only allowing algorithms which are not too sensitive to changes. And what it means is that I give you the graph, you give me a solution. Let's say I give you a graph with one edge modified, deleted or added. What I want you to do is to give me your solutions to be pretty much the same as before, maybe slightly modified. I don't want you to reorganize the solution in some crazy way. Well, some algorithms have these features, some algorithms don't have these features. So you might say, why restrict yourself to those algorithms? One reason is that those algorithms are those who succeeded up until the thresholds that we found. So this is a reasonable class of algorithms. Well, it turns out that those algorithms cannot overcome the barrier for the following simple pictorial reason. You use your algorithm, you produce a solution. You use the algorithm for the next instance, you produce a solution. As you move between graphs, only one edge is changed at a time. I've deleted the graph, but all of those graphs are connected by a chain of one deletion, one addition at a time. So your space of solutions should be continuous, rather continuous, because the algorithms are not very sensitive to edge deletion edge. So that means that these points should evolve in some continuous way, but if the algorithm is correct, it cannot be continuous, it should jump, because the correct solutions are clustered. This is effectively all continuity versus discontinuity idea. You're trying to fit a continuous function that connects two disconnected, topologically disconnected sets. This is all in discrete geometry, so continuity versus discontinuity is not literally continuity in the sense of analysis. It's more like Hamming cube. But the idea is rather similar. Solutions live in disconnected sets, and you're trying to fit a continuous path between them. You cannot do that, so the algorithms are doomed. And that's the whole idea. The proof, as I said, the proof ideas is all first and second moment, nothing super sophisticated. Go to the book and learn this important method if you didn't do it already. And now let's slowly wrap up. What I want to do now is share with you at a high level of where we can take this to and what we have learned since then. And then I'll wrap up. Can this geometry, by geometry I mean this property, this continuity, overlap gap property, clustering, things like that, can it be used to predict the onset of hardness? So what do I mean here? This property and the proof that the property is a barrier to the algorithms was successful, but only near optimality, in the sense that it ruled out the success of algorithms within some proximity to optimality. But our failure was, in fact, in a different location. For the hard spheres, it was half optimality. This method didn't give half optimality. It gave more like 10% proximity to optimality. We could pull off. Half optimality we could not back then. That was annoying. But it was fixed in a remarkable paper about the same year by Raman and Dirac, who said, you know, we don't need to look at just pairs of solutions. Let's look at more complicated tuples of solutions. And they introduced this idea of multi-overlaps. In some way, I'm not going to bother you with details, but at some level the idea is similar. And they said that if you look at the multi-overlaps in geometry, you can actually go all the way to half. And they explained this half failure originally put forward by Karp in 1976 by this multi-overlap geometry. In again the same way. Algorithms insensitive to changes of the graph cannot beat the half. And what it means is that either the algorithms simply do not exist, fast algorithms, polynomial time algorithms do not exist, or you really have to come up with brand new algorithms which somehow are not very sensitive, which somehow are sensitive. Okay? Long story short, this idea of multi-overlaps actually was productive across all problems that we could analyze. All the times it was predicting, and sometimes this was ahead of actual algorithms. It told us where the algorithms should stop. So you look at the geometry first, and then you know, okay, based on this geometry, we predict the algorithms will be successful only up to here, but not beyond. One remarkable, and perhaps the most remarkable example of where this happened is back in the physics example of the spin glasses. The physics example. By the way, I never explained the word glasses. It actually is in reference to glasses, the glasses that you can break. The spin glasses is a physics theory to explain the conundrum in glasses. The conundrum is that nobody agrees if it's a solid or liquid. But I really don't understand fully what's the physics side of it, but computationally we understand. And what we understood, remember that this crazy formula for optimizing over Gaussians, this is the optimal value. There's a little word here that I didn't highlight. It says increasing. This is optimization over increasing functions. Why it's important is that if you replace increasing by the word all functions and solve the same optimization problem, that actually gives an algorithmic threshold. And in this fairly recent paper by two computer scientists, I want to stress that these are not physicists, mathematicians and computer scientists. They said if you replace this increasing by O, you find a number. It is lower than the original number. And that is the onset of algorithms and algorithms' hardness. Up until this number, algorithms exist and they exhibited one. And above this number, algorithms fail. So this was perhaps the first time where change in the geometry was predictive of the algorithmic hardness. And that's quite exciting. This is a new phase transition, was apparently not known and not predicted in physics. The literature in physics on spin glasses is huge. It was hard to imagine that there is anything they would not predict in the past, but not this. So our physicists must be excited about that. Just a quick comment about the fact that, since Thomas kindly mentioned quantum algorithms and machine learning, in fact, this development had a segue in both worlds, in the sense that certain algorithms that machine learners and quantum theorists proposed as a way to solve problems of various kinds turned out to be didn't pan out because these algorithms that they proposed were insensitive, and therefore they probably don't overcome those barriers. They didn't know about those barriers, so they were hopeful based on simulation that they will do something good. It does not, because barriers are not broken, apparently in their approach. Bad news. So now let's wrap up. Let's see how the conversation went between our two scientists. Computer scientist said, I'm a computer scientist, I'm interested in computations and algorithms. Is there anything in physics you can tell me that I didn't know that I might find interesting? Why should I talk to you, in other words? And the answer could be like this. Yes, I can help you. When you have difficulties finding algorithms, blame the geometry. Blame the change in the geometry. This is where you need to look. Change in the geometry creates energy barriers. Energy barrier is a physics term. It has to do with optimization. Energy is a cost value. It's just a physics lingo. Change in geometry is to blame. You can predict where you're going to be successful or not successful in constructing an algorithm simply by looking at where the phase transition occurs. Roughly speaking, liquid to solid. Structure versus chaos. But likewise, okay, I helped you, how are you going to help me? And the computer scientist responds, yes, you're interested in this strange matter called spin glasses. I can understand it now. I can tell you that near optimality, the near optimal energies in this strange matter will behave differently for two-spin system and more than two-spin system. Interaction size matters. Right? What's the physical significance of that is for you to decide, but I can tell you the phase transition you didn't know before. Take it from here. Moreover, now that's last segment is something I did not highlight in the talk, but it's for the offline discussion perhaps. Moreover, as this model equilibrates in the physics sense, the system is likely to stay below the phase transition, which by the way was discovered by computer scientists. So in a way, computer scientists paid back to the physicists by discovering a certain phase transition which has a physical meaning that was not known by physicists. So it's a mutual conversation and mutual collaboration. Good, now they can shake hands and go have a drink. That's the end of my talk. Thank you very much.